The recently released images of the interstellar object 3I/Atlas on November 5, 2025, have deepened the scientific intrigue surrounding this unusual visitor to our solar system. Unlike typical comets, which normally display a well-defined tail of dust and gas pushed away from the sun by radiation pressure and the solar wind, 3I/Atlas continues to present itself as a compact and nearly featureless point of light. The new images do not reveal any clear cometary tail, nor do they show the extended and asymmetric features one would ordinarily expect from an object actively losing mass during its close passage around the sun. What makes this more puzzling is the fact that its coma, the diffuse envelope of material that often surrounds a cometary nucleus, appears almost identical to its appearance in Hubble Space Telescope images taken months earlier on July 21, 2025. One would anticipate substantial changes after perihelion, especially for an object experiencing significant non-gravitational forces due to outgassing, but the morphology remains remarkably stable, offering no obvious signs of the dramatic mass loss inferred from its measured motion. A detailed analysis of its orbital behavior reveals a transverse acceleration of 3.7 times 10 astronomical units per day squared, directed perpendicular to the sun-object line. Such a measurable deviation from a purely gravitational orbit is usually interpreted as evidence of outgassing. When volatile materials vaporize from the surface of a comet, the escaping gas exerts a recoil force on the nucleus, a consequence of simple momentum conservation. Based on this principle, the magnitude of the observed non-gravitational acceleration suggests that 3I/Atlas must have expelled a substantial fraction of its mass during its passage near the sun. In fact, by applying the standard momentum conservation formulas used to study cometary outflows, one can derive that the object would need to lose more than 13% of its total mass to produce such an acceleration. For a conventional comet composed of ices mixed with dust and other volatiles, losing over a tenth of its full mass in such a short period would undoubtedly lead to the development of an extremely conspicuous coma and an extended dust tail, both of which would become brighter and more structured as the object moved farther away from the sun. Instead, the opposite seems to be happening. 3I/Atlas continues to show only a compact source of light, with no significant brightness enhancement, no extended features, and certainly nothing resembling a typical cometary tail. This stark contrast becomes even more striking when compared with the recent observations of Comet Lemon, captured by the same telescopes and under nearly identical conditions only 2 days earlier. Lemon displays exactly what astronomers expect from an active comet: a broad, bright tail stretching away from the sun, shaped by the continuous release of dust and gas, and sculpted by the combined effects of radiation pressure and the solar wind. The difference between the two objects is dramatic. Lemon behaves like a textbook comet, while 3I/Atlas behaves like something entirely different, resisting the usual interpretations that apply to icy bodies undergoing sublimation. The absence of a tail in 3I/Atlas cannot simply be attributed to observational limitations, instrument sensitivity, or geometric effects, because the same equipment easily detected Lemon's extensive dust features. This reinforces the idea that 3I/Atlas is either losing mass in an entirely different way, or perhaps not losing large amounts of traditional volatile material at all, despite the strong non-gravitational acceleration indicating otherwise. The combination of strong acceleration and a lack of visible outgassing is one of the central anomalies that make 3I/Atlas so intriguing. In ordinary comets, sublimation produces jets of gas laden with dust particles, which scatter sunlight efficiently and create visible structures. If 3I/Atlas were undergoing sublimation at the level implied by the derived mass loss fraction, its environment should be filled with dust grains, micron-sized particles, and ionized gases. These materials would produce an extended coma many thousands of kilometers wide and a tail stretching over hundreds of thousands of kilometers. These features would grow even more pronounced as the comet moved away from the brightness of the inner solar system, because the dust would remain visible even as the nucleus cooled. Yet nothing of the sort is seen. Instead, 3I/Atlas appears almost asteroidal in its appearance, showing a stable, concentrated point of light and lacking any sign of dust-related scattering in its vicinity. Another layer of mystery comes from the timing. If the mass loss occurred predominantly during perihelion, the object should now be surrounded by the debris it expelled only weeks earlier. Dust released near perihelion does not vanish quickly. It remains visible for long periods, slowly drifting into the characteristic curved shapes that trace the object's recent path. The persistence of a clean, dust-free appearance strongly contradicts the 13% mass loss estimate unless the ejected material somehow failed to produce visible particles. This would require highly exotic behavior, such as mass ejection dominated by ultra-fine gas molecules with virtually no dust component, or the loss of material in forms that do not interact with sunlight in normal, detectable ways. Neither possibility aligns with standard cometary physics and would require new theoretical explanations to make sense. Furthermore, the similar morphology between the July Hubble images and the new November observations introduces another complication. If significant mass loss activity had been ongoing as the object approached and then passed perihelion, the appearance and shape of the coma should have evolved noticeably over the span of several months. Cometary surfaces undergo rapid changes under intense heat and radiation, developing jets, fragmentation events, and evolving brightness profiles. The fact that 3I/Atlas looks essentially the same 6 months apart implies a surprising stability that is inconsistent with the forces inferred from its motion. This raises questions about the object's structure. Perhaps it contains unusually strong materials capable of withstanding extreme thermal stress, or perhaps its outflow processes occur in a distributed or isotropic manner that fails to produce the jets normally associated with acceleration. Alternatively, the mass ejection might occur as invisible gas, devoid of dust, escaping from subsurface layers through microvents too small to create detectable features. These possibilities are scientifically fascinating but highly unconventional. The interstellar origin of 3I/Atlas adds yet another dimension to the puzzle. Since it comes from outside our solar system, its composition, internal structure, and evolutionary history could differ greatly from those of objects formed around our Sun. Interstellar objects are exposed to different radiation environments, cosmic ray bombardment, long periods in deep space, and potentially extreme thermal cycles. These factors might lead to unusual material properties, such as superhard crusts, depleted volatile layers, or exotic compositions not yet observed in local comets. The absence of a visible tail could therefore reflect a surface that no longer contains dust or conventional ices, even if deeper layers release gases through small fractures. This could also explain why the spacecraft detected forces do not correspond to observable coma features. The gas might be escaping in tiny amounts sufficient to alter the motion, but insufficient to scatter sunlight effectively. Even so, for more than 13% of its mass to have been lost invisibly remains difficult to reconcile with our current understanding. All of these anomalies make 3I/Atlas one of the most intriguing and challenging objects studied in recent years. Its behavior does not fit neatly into any existing category. It accelerates like an active comet, yet it appears like an inert body. It should exhibit dramatic post-perihelion dust structures, yet it remains compact and dust-free. It should evolve in morphology under solar heating, yet it maintains the same appearance over months. The comparisons to Comet Lemon highlight just how dramatically it deviates from normal expectations, reinforcing the idea that 3I/Atlas may represent a new class of interstellar objects with physical characteristics far outside the familiar range. Whether it is composed of strange materials, has undergone unusual evolutionary processes, or interacts with the Sun in an unconventional way, its anomalies challenge current models and compel researchers to revisit assumptions about how interstellar objects behave. As additional observations are collected and analyzed, 3I/Atlas may ultimately help expand our understanding of the diversity of small bodies in the universe and the physical processes that shape them.